Here's another example of using the constant acceleration equations. Here we have a parachutist who is flying in a plane, and she steps out of the plane, and she is falling towards the ground. And so we can imagine she's falling, and after she's accelerating downward because of gravity, and at a certain point she lets go of her parachute, and so then she'll start continuing to go downwards with her parachute, but at much more slowly than she was at the beginning. And so in this case, she's having there's actually two parts to this problem, because for the first part, the parachutist is in free fall and she's falling due to gravity. Later on, once the parachute opens up, she decelerates at a different acceleration. So at first blush, it seems like there's two different accelerations here, and thus the acceleration is not constant, and that's true. But what we can do is consider the free fall as one set of motion, and then the motion of descending with a parachute as a separate motion. In this situation, the total time would be the total time elapsed during free fall plus the total time of descending with a parachute. The final velocity of the free fall would be the initial velocity of the descent with a parachute, and then the total distance traveled would be the sum of the two distances. So in this case, we can consider this as two separate consecutive constant acceleration problems. And when she initially steps out of the airplane and freely falls, we can use our kinetic equations to better understand that. So we know we have the kinetic equations, the kinematic equations. We're told that she steps out of the plane, and by that we mean she's not jumping up and she's not jumping down. If we're talking about motion in the y direction, a vertical motion, then her initial velocity would have to be 0, because she's not going up or going down. Her vertical velocity is 0 initially. Her acceleration is negative 9.8, because that's due to gravity. And we know that she freely falls 50 meters, we're told. So her displacement in that time is a negative 50 meters, because she ends up 50 meters below where she began. What we're interested in is how long she's in the air, which is the amount of time. So we'll need to know the time frame associated here. We also want to know about the height that she jumps from. In this case, we know part of the height, so we don't have to calculate that directly. So we'll begin by looking for the time, while we want to avoid using the final velocity for now, because these are the other kinematic variables that we know. So our equation that doesn't have final velocity is this one. We can plug in our values. We see that the 0 initial velocity cancels that term out, and what we can find here is that the time that she falls is 4.5 seconds. That's all the information that we need. If we're interested in the time in the air, we've just found time. We're interested in the height of the fall. We know the height for this part of her motion. So we can go on to the second part of the equation, or the second segment of her trip, the second constant acceleration. In the second constant acceleration, we say that she decelerates at 2 meters per second squared. So again, if we have a constant acceleration, we can use our constant equation variables. We're told that she decelerates, So that means she's slowing down, but she's going downward. And so if her speed is getting less as she goes downward, the sign of the acceleration has to be positive 2 meters per second squared, which makes her velocity less. We are also told that she reaches the ground with a speed of 3 meters per second, which is a safe enough value. 3 meters per second, but she's headed downwards, so that will be a negative 3 meters per second. And if we're interested in the total time in the air, that means we need to find time. We're interested in the total height of the fall, that means we need to find the displacement as well. What all of this tells us is that to find these two, we need 3 kinematic variables. We only have 2 right now, and v naught, the initial velocity, is the only one left other than the ones that we want to calculate. So if we need to find the initial velocity that she has when her parachute opens would be the final velocity that she would have as she's free falling. So we can come back to the initial part. We found time. We can also find our final velocity as well. So here we want to avoid time. That's our calculated value. We want to use the values we were given instead. The equation there is v squared equals v naught squared plus 2 times a times our displacement. Here we have v squared is equal to 0 squared plus 2 times negative 9.8 times a negative 50 meters of displacement. And that gives us our final velocity here as a plus or minus 31.3 meters per second. That's the final velocity when her chute is opening, so that is her initial velocity for her descent with a parachute. The only thing to think of is that that plus or minus comes from the square root. We have to use context here. She's headed downwards, so her velocity has to be a negative amount. So if we're interested in in her displacement, we can find that through the same equation as before. V squared equals v naught squared plus 2 times the acceleration times the displacement. This is 3, technically negative 3 squared is equal to negative 31.3 squared plus 2 times 3 times our displacement. And our displacement there is a negative 161.8 meters. So we expect it to be a negative amount. She's falling downwards with her parachute, so she should end up below where she began. If we're interested in the time, we can also use the values that we were given, and we can say that the final velocity is the initial velocity plus a times t, so negative 3 equals a negative 31.3 plus positive 3t. Oops. This should be positive 2. And so we can find, again, the time. T is equal to 14 seconds. So now we have all the information about the initial free fall. We have all the information about the descent with the parachute. If we want the total time that she's in the air, she initially falls for 4.5 seconds in free fall. She descends for 14 seconds with her parachute. That means it's a total of 18.5 seconds. She initially falls 50 meters while she's free falling. She falls another 160 meters with her parachute. So her total displacement, her total descent will be 211.8 meters, and that will be a negative amount, meaning that she ended up that far below where she began, if assuming that the airplane is a zero height to begin with.